Espérons. I have no idea. I can't remember. We're only there for one night. We hope it's good. I think it's enough. I think so. No, it's not far from Luxembourg because I need to go shopping. So I always choose it within range. You're on Zoom. That's good. All right. How are we doing? What's that?
What's that? Maybe a pointer. Maybe I can get his pointer.
Yes.
He's left.
He's I'm sorry, you'll have to use your mouse.
Not a fancy green one.
Oh, thank you. Okay, so I think 2 years ago, Andrei was on his way here, but then I think COVID stopped him from actually making it from Donostia over to London. So we're really happy that this time he made it. And he's going to tell us today about his ongoing work on twisted bilayer graphene and the heavy fermion scenario that he pioneered. So we're really delighted. Welcome, Andrei.
Thank you so much for having me, and thank you for inviting me again after I was in last time. London is amazing, and let's try. So I'll put this thing here. This is the Finway spectrum. Okay, supposedly, there's a real goldstone, but then there's like this very low lying flat band mode. So maybe low density but high density state of magma. So okay, can you hear on the Zoom? I think they weren't hearing because I was muted. Okay, good. So I wanted to talk a little bit about some new developments in what we've been trying to do collectively with many people over this heavy fermion model for twisted bilayer graphene. Most of this work has actually been done by Dimitri, who's here, whose internet I'm actually using currently. But if it doesn't work, if the theory doesn't work or the internet doesn't work, blame him. Second person who's done most of these things is Jonah. And how are you? Or how are you and Jonah collectively? We've benefited from a lot of help from the DMFT group of Rosa Valenti, George Sandrivani and Tim Welling, Gautam Ray, Lorenzo Kripa, several other people, and the experiments that I'll be talking about are done back here when we're talking about Dima's experiment, because it required a little bit more going into details. But we're talking about some recent stuff that Eva and Stefan have been very nice to share with us in terms of their experimental discoveries. These are the students in the group that were working on this, and we've benefited from a lot of collaborations and talking to all the senior people here that I haven't put their pictures because I've only put the pictures of the junior people. Now, I think the the internet's not the problem, but my computer seems to be the problem. Okay, let's see. Okay.
The presentation, by the way, is not being shared properly with the Zoom.
Oh my God.
We're seeing the something else, the notes or something.
Click to add notes. Oh, this is not good.
Yeah, that's what we're seeing. The click to add notes.
How about now?
Well, yeah, that's okay. Though it would be nice to have what we're seeing on the main screen. That's
Well, I'm still seeing something from here, the window, just the entire window, you mean? Okay, just the desktop. Because okay, good.
Good.
This is,
Hit A and see if it comes up.
let's see. Okay, slideshow. Play from current slide. What do you, is it
Great,
good?
perfect.
Oh,
Yeah.
fantastic. Okay, thank you. So the subject of the talk is going to be some work on systems where interactions are larger than dispersion. Now, there's two types of these systems, roughly speaking. One of them being purely atomic, where you have a lot of potential wells that are very deep, where the electrons cannot tunnel in between them, and that gives you zero dispersion or very weak dispersion because of weak tunneling. In that case, you can get, for example, TJ models and antiferromagnetism, really. But in another type of system where you have the flat bands due to interference or quantum interference, where you can, for example, see in this leaf type lattice that the dispersion is actually very large, because, or the hopping is very large because you do have dispersion in some directions, but in some directions you don't, then the flat bandness is coming from interference, from wave function interference. Some signs of the wave function cancel as the electron hops around the lattice. And then in these systems, you can have interactions. You can have hopping of the electrons, so you can have things that don't commute, unlike in the system where, for example, if I just have the atomic limit with a large Hubbard U, then the Hamiltonian will be classical. Here we can still have some hoppings and some things that don't commute, such as interaction kinetic, but the interactions can be much stronger than the kinetic energy because the actual dispersion cancels in some directions. Now, we don't want to talk about stoichiometric systems. The reason why we don't want to talk about stoichiometric systems is because they are very complicated and show up as a spaghetti of bands. So even if you have some flat bands at the Fermi level, like in the Kagome metals, you have a lot of other bands at the Fermi level. And the problem with having a lot of other bands at the Fermi level is because then you cannot distinguish what comes from the flat band from what comes from the dispersive band very clearly. So we don't want to talk about that for now. We want to talk about 2D materials and 2D flat bands, and kind of the paradigmatic model for this is the twisted bilayer graphing. I started, of course, looking at flat bands kind of late in the game, but of course, people such as Eva and Emmanuel and Pablo and all these people that are written here started much earlier thinking about flat bands and what they would do, and basically realized that they would be a great playground for interactions and nice physics. Now, what the twisting does, so you take this layer of graphene, 6 electron volts dispersion, single layer, you put it in a twisted configuration with an angle of 1 degree. It basically starts renormalizing the bandwidth of these Dirac fermions, creates gaps, as you can see, and this bandwidth is renormalized 1,000-fold or more than 1,000-fold from 6 electron volts to 6 me-electron volts. The interaction is of order 30 me-electron. You can just take the, the E squared over the moire length, and that gives you a scale of the interaction, and that's order 30, 50 me-electron volts, much larger than the bandwidth. So you're in the strongly interacting regime. Now, there's of course a beautiful model that early on
You may need to click on that turn of volume.
Sorry, turn up volume.
Should,
Should I turn it up?
no, just.
No.
On the X side
There's the X.
and the OK.
The problem is I don't have the X here. There's only some X's on some of the screens.
You got it, you got it.
No, I didn't. That's you see, I'm clicking on it, but it doesn't want to click on it. It's actually clicking. See, it's fake clicking. I think we're just gonna have to do it's see, the problem is you're clicking on it, but it doesn't want to click it. Let's see. Escape, turn up volume. Okay, now it okay, very good. How about this?
The other one, OK as well.
You see, this is the problem with asking for permission so many times. Just okay, let's see. This is it's a bit annoying, huh? No. Okay, let's see. Is it working?
Fantastic.
Okay, great. No. All I need now is some Princeton update. Okay. So the continuum model, the TVG model is very simple. I will try to argue that it hides kind of nice complexity beneath it. That's pretty very interesting. So, for example, in this model, in the continuum model, what you do is you take the lower layer of graphene with this Dirac point here. This is the Dirac point. The upper layer of graphene with this Dirac point here. Okay. There's another valley. This comes from the K point of the lower layer, K point of the upper layer. There's another valley conformal from K prime point, and then you put in a tunneling term in between the layers, this TFR, which has the periodicity of the superlattice of the Moiré structure. And this is in the simplest models that don't have relaxation, strain, etc. This is just a term that's got the first harmonic, and this is the first harmonic model. Works pretty well for such a beautiful and simple model. The first harmonic model has modulations at the Moiré length scale, which is really the length scale in between the K vector of the upper layer and the K vector of the lower layer. Now, I would like to argue that this model hides heavy fermion physics. And let's try to argue this, or let's try to derive it rather than argue. First of all, this is how the band structure, you take that model, you solve the band structure. This is the Moiré-Briand zone. This is how the band structure, the single electron particle spectrum of that model looks like. You can see here two flat bands. They look very flat. There's some dispersion around the gamma point. You can see two flat bands around charge neutrality or around zero energy. The spectrum is almost particle Hall symmetric. In this particular model, it's exactly particle Hall symmetric, but it's in general, it's almost particle Hall symmetric. You know roughly the energy that you're at just as you start from the Dirac. Now you're at energy zero. And then there's two quantum numbers, valley, which is this K prime, K of the lower layer and K of the upper layer, and K prime is the lower layer and K prime is the upper layer. They don't talk to each other in single particle because there's a huge momentum difference between them that cannot be met by stacking a very low number of Moiré-Briand zones, because the Moiré-Briand zone is small. So this is a good quantum number value. Their spin also, we don't have spin overcoupling, or it's very low in graphene. And that means that you multiply this by 4. So that means that these bands can take up 8 electrons. Okay. And then this means that in this case, you go from -4 electrons to 4 electrons per Moiré unit cell in these gaps. There's 8 electrons here. The counting, this is just conventional from -4 to 4. And of course, the system is a bent metal from any -4 to +4 electrons. But of course, because you have interactions, this is how the phase diagram looks. You get these large insulating type resistance behavior at integer fillings. Okay, and in between them you get superconductors. So that's clearly a hint of the fact that the system is strongly correlated. Now, I think the next step that you want to look at experiments just from a bird's eye view is there's two types of experiments. There's experiments that basically show kind of a juxtaposition between two different types of of behavior in these flat bands. So now we're going to talk about these flat bands of twisted fiber graphite. First of all, if you look at STM type experiments, and I think this is STM by Eva, this you can clearly see that on the Morris scale, you have a system that looks like localized charges, right? These are in the flat bands, you just look at the charge density, and it looks like you've got very localized charges on the Morris scale. On the triangular lattice, there's some, C3 symmetry breaking a little bit, whatever, but in general, those are, we'll come back to those details a little bit later, but in general, it looks like you have quantum dot behavior on sites of the triangular lattice on A sites. And then I didn't show it here, but you have other experimental papers that basically show kind of the presence, or what we believe might be the presence of local moments. I'll come back to this later to get to quantify it more in a recent experiment and understood. Yes.
Just to get the questions rolling, do you see susceptibility, or do people see susceptibilities, pure type susceptibilities?
I don't think they've done susceptibilities, because I think it's a problem to in
Oh, I see.
sample.
So, but for
So-
example, something like that, that's a signature of local.
I don't think they can't do pure. I agree. They can't do. So I think that would be, that's but the only, so you'll see at the end, or trust, not trust, but the 80% of the top, when I'll show you the Andrei's who measured, Andrei's who measured entropy, and we see log of,
Log 2.
well, there's some eightfold returns, so log 8 and log 4 was traced to.
Okay.
So we'll get to that, but susceptibility, which would be kind of,
Well,
as you say,
that's-
hasn't been done yet. But hopefully with these new techniques. Okay, so so basically, then you have these type of experiments which, show superconductivity. Then you put the system in field, you see Chern insulators at some small field. You even see fractional Chern insulators at field induced a little bit with a little bit of field. So you can see kind of just the juxtaposition of two types of systems. And there's an abstract of a paper, I think it's Shahal's paper in 2019 or 2020, that says that the correlated state features contradictory properties, some associated with itinerant electrons and others associated with local moments. So that's not how we got to this model. The way we got this model, we solved it in the continuum, and then saw like a charge to bound state. That basically means that you have two heavy fermions on the site. But this is how I like to present it, that if you take the experiments to face value, then you should see some localization in them. And then you can think about it a little bit more and take them to more face value. And if this is the continuum model band structure, you immediately know that if the gap from a band to any other bands is large, okay, then that band can only be triple. Okay, that's kind of a theorem that you can prove of Vanya's things. Steve Kibble from a paper that's from the 1980s proved that 1 over the gap is bounded by the Vanya spread. So if I have infinite gap or large gap, the Vanya spread has to be very tiny. So you get insulating behavior, and you get no, you get Vanya states that are purely localized. So if the gap is very large to other bands, i.e. there's no Berry curvature, because Berry curvature is interband transition, everything is localized. So you can see, you can look at this model and see that for most of the Briand zone, the gap is quite large. In fact, this, is quite large at these energy scales, more energy scales. This is roughly V Dirac, which is the same velocity as the Dirac graphene velocity, times the Moire scale, 100 electron volts, Coulomb is 40, okay? So low energy physics happens here. Most of these bands are far away from any other bands. They have no Berry curvature, and you can, kind of do this computation and prove that. The only place where there is a Berry curvature is where the place where the bands start getting close together, because the matrix elements of transfer between the bands are hopping between, the number R can be large. And in this case, the Barry curvature of these flat bands is actually localized. It's a non-abelian Barry curvature because the imaging system don't allow just the trace part. So there's some non-abelian version of it, but it doesn't matter. It's very much concentrated around the gamma point. Now, you can also prove that if you look at these two bands, which per value per spin are the low energy bands of twisted binary graphene, then there is no Vanier description, no localized description of them. The reason for that is, we can go through it more deeply, but basically you have for every symmetry group nowadays tabulated on a Bilayer crystallographic server all the symmetry eigenvalues for the bands that come from atomic limits, because you can just induce them. You can just put delta functions on atomic sites and then compute the eigenvalues. You cannot say that, for example, there's gamma 1 and gamma 2 or gamma 2 or gamma 2 and gamma 1. You cannot say their order, but if a band is made from atomic limit, you know its eigenvalues. And you go on this Bilayer crystallographic server and you see that these bands can never be an atomic limit. And the problem is that there's an obstruction to them being an atomic limit because of the wrong eigenvalues at the gamma point. These bands, these gamma 1 and gamma 2 are some eigenvalues under some C2 representation. They're the wrong eigenvalues for an atomic band. You can also think of it more physically by the fact that these bands really come from the Dirac node of the lower layer and the Dirac node of the upper layer, which have the same chirality. They're both at the K point. There's another set of bands at the K prime point, which have the opposite chirality. Together, the system is trivial, but they don't talk in single particle. So per value, it's non-trivial. So this is very clear. This non-triviality in the Bistomic-Long model is actually a strong topology in the sense that whatever number of bands I can take, I'm not going to be able to make the system trivial. The way to make the system trivial is to couple it to the other value. This system is a continuum model that's topological at any bandwidth, okay, because the continuum models don't have a real space description. You can get to the other, or some of them, this one doesn't. For example, if you couple it to the other value, you can, but they're decoupled. So per value, this system is a topological set of bands with zero Barry curvature somewhere here, and a lot of Barry curvature at the gamma point because of this fact that there's a small gap at the gamma point and a larger gap everywhere else. Also, we know that this is how topological insulators come in by band inversion. All the actions happens where bands touch or where bands get closer together. So there's no Vanier orbitals of this band. So there's no way to just get purely the description that Eva and other STM groups were seeing of these blobs. But there's almost that way of getting it, because if you now think about the fact that this velocity, this remote Dirac band velocity grows very fast, then you're going to realize that most of this flat band doesn't have any Barry curvature, and hence most of it is.
I have a notational question. So
Yes.
what is the subscript on the gamma points referring
The
to?
gamma 1 and gamma 2 are the two representations of C2x. They're C2x squares to 1. They have eigenvalue plus or minus 1. They're just some crystallographic representations, which you can get them from a website.
Okay.
They're just nomenclature.
But they're not like different layers, right?
No.
Okay.
No, they're bonding and anti-bonding of layers, for
Okay.
example. Very good. They're just, all of these have some, this, for example, is a double representation. It's just the Dirac node that's here. You can't see this Dirac node because it's too flat, but there's a Dirac node. It's just nomenclature of representations. That is not, the only thing that's crucial is that these eigenvalues cannot form an atomic insulator, but you can almost form an atomic insulator, meaning that if you're looking at these blobs that you can see in STM images on the triangular lattice and try to build bona fide Vanier states out of these blobs, you can do it, and you can ask what's the overlap of those states after you make a Vanierization and you make them, most localized. There's a whole procedure that we can do. You ask them, you take those ansatz states and you ask what's the overlap that they can have with this set of two flat bands. and you get 95% overlap. You can't get 100%. The reason is because, well, these bands are topological, so they're never going to be able to be destroyed by localized orbitals. Also, there's another reason. These Vanni orbitals, which have this representation, they sit on the triangular lattice size, they have this representation, or we're going to call them by abuse of language F electrons. They are of a different representation of the gamma point. They have a gamma 3 representation rather than gamma 1, gamma 2. They have a double representation rather than two one-dimensional representation. Their overlap with these flat bands has to be 0 at the gamma point. But it's 95% because everywhere else is very large. Okay, so we found out 95% of the system. It's some localized orbital that preempts the the question of where the interaction goes. It's going to go mostly on these orbitals, but they're not highly localized. So then, what is the other set of 5% or 6%, depends on what of the bands? Well, what you can do is you have this Bister-Macdonald model that looks like this, continuum model. You know that 95% of it is these F electrons. You can take a projector of these F electrons. You can take 1 minus the projector in this F electrons. That should represent the 6% that's left over. And you can dot this in between the Bister-Macdonald bands and find the Hamiltonian of the leftover piece. That's how you do it mathematically. You can also do it by symmetry and ask what's the Hamiltonian of the remaining piece. You can do it by many things. You can derive it. And you find out that the Hamiltonian of the remaining piece is just an AB untwisted bilayer looking fermion. Okay, so AB untwisted bilayer, i.e. something that lives in between these AA sites, the AA sites of triangle, has this double vortex here, as the AB lattices have. This double vortex here, and this sort of gapped states here and here. Now, this gap normally in the AB is of over 300 electron volts, which is just the hopping between these. In this case, this gap between this state and this state of what we're going to call the C electron is of the order 8 electron volts, which is just the bandwidth of this Bister-Macdonald model. Okay, so topologically, it looks exactly the same as the AB. It sits in between these AA sites, but it's got different, it's got the same velocity as the Dirac fermion, but it's got this small gap of 8 electron volts between here and here. Okay, so then you ask, well, what you've told me is that this there's a heavy fermion which is on triangular sites, and then there's this C electron, which is dispersive electron. By the way, this double vortex here is the reason why the topology of the system hasn't really changed, because I told you that these bands were topological, but these F electrons are not. So where did the topology go? Well, the topology actually got pawned off onto this double vortex here in the following way. So what you can say is, okay, well, now let's build a Hamiltonian for it. Let's actually write down the Hamiltonian. These F electrons that sit on a triangular lattice, when they hop from one lattice site to another, they're very localized in 0.2, the Moira-Brilliant zone, Moira unit cell, sorry. Moira unit cell here, 0.2. So their hopping is actually 0. Okay, they have no hopping. So this is the heavy fermion block, 0 hopping, direct hopping between them. So they actually form a flat band. There's 1 per Moira unit, well, 2 per Moira unit cell, px plus minus I dy, we call them F. They form a flat band. This guy, which is the C electron, looks like this. For example, this M is just the difference between these two representations. This is this 4x4 block, 2-dimensional representation, 1-dimensional representation, 4x4 block. Okay, and it looks like this, right? So I have a two flat bands and something that looks like this. This doesn't look anything like this Bister-Macdonald model. So how is this equivalent to this? Well, there's another term that you don't put in by hand, you derive. What you do is you take the wave function of the C electron here at the gamma point. You take the Bister-Macdonald Hamiltonian and you dot it into the wave function of the F electrons also at the gamma point. The F electrons and the C electrons at the gamma point are actually the same representation. This is gamma 3. This is also gamma 3. There's two-fold germ. These are these two representations. They're going to bind and anti-bond, bond and anti-bond. Okay. They're coupling because they're the same representation. They're coupling, and the representations tensor torque contains identity. The largest coupling that you find is just a constant, okay? Which is just the constant between these F electrons and this double vortex of the C electrons. That splits this double vortex up, down. These remain, okay? These gamma 1 and gamma 2 remain. These are just the representation that we spoke about before. This is gamma 1, this is gamma 2. But the double vortex here has interacted with the two-dimensional representation of the heavy fermions, has moved up and down. And now this is how, just by deriving this, because you can derive it from you can derive this number from Bristol and Brown model, this is how good the match of this model is with the Bristol and Brown model. The reds are this model, the black lines are the Bristol and Brown model. At low energies, the match is almost perfect. And this is not just dispersion, also charge density, etc. It's very good. Of course, it's going to mess up at higher energies. I can get the agreement to be even better, even at higher energies, by adding more terms in the K dot B expansion of this double vortex fermion, but we don't need to because we want to access these energies anyway by Coulomb interaction. So this is good enough of a model for low energies. So the only thing we've done up to now is a unitary transformation between the continuum degrees of freedom of the Bistrom-McDonald model and some degrees of freedom that separates the physics into some localized, almost delta function, like the Gaussian, but almost delta function, like very localized, heavy F electrons with no topology, and a double vortex C electron whose topology, the topological symmetry, is protected by symmetry in the symmetric state. This double vortex can never be split unless you break some of the symmetries of the problem. And the match is perfect. Yes.
And what is the Coulomb interaction between the original electrons and their new electrons?
Right. Very good. So this is the next slide.
Oh,
Good,
okay.
very good.
Okay.
Yes. So this is so this is the non-interacting picture,
Yeah,
right?
that's what it is.
You just made the unitary transformation. Now this unitary transformation would be just useless if
Yeah.
there's not some gain. Right? And the gain comes because you can now take the screened Coulomb interaction because they have some gates, depending on the gates, screen distance, etc. You take the screened Coulomb interaction and then you project it onto this basis of heavy and light electrons. And then you find that the largest term, as would be expected, is an on-site Hubbard loop of these F electrons. So now we have the heavy fermion picture with the interacting heavy fermion, because now you've basically found a basis where your interaction is localized, is local, right? Now, if one could do exact diagonalization or, theory, exact theory, one could just use the case-based description, which you can do, but in the case-based description, for example, if you don't have this local description, you can't get the Hubbard bands. Okay, so these are the advantages of actually having this local description, because you can get things that you can never get in just the case-based description, because you can only do Hartree Fock on main field. You can do exact diagonalization, you can do it for a small number of sites. So now we have at least a Hamiltonian where we separated the local degrees of freedom, and this now becomes the largest energy scale in the problem. Now there's some other energy scales of the problem that are large, but they can be treated at mean field level because they couple the F and the C's are dispersive. So, but this is the largest energy scale of the problem in this model if you derive it.
Quick question. I may have misunderstood something, but I was under the naive impression that the F electrons were some 95% of the electrons in the system and some remaining 5% of the C.
Yeah,
So how does the hybridization work in the band restructuring?
right.
Have such a difference.
Yeah, very good. So that's a very good question. So yeah, the hybridization it's here, right? But it's mostly active at the gamma point, right? Being away from the gamma point, this V star is so large that these shoot up, and you're not going to see very much here, right? Basically, here it's going to go with gamma over V squared. So by the time you reach So gamma is roughly 24 milli-electron volts. V star times the Moire unit cell is 100. So by the time, so, uh-oh, I'm telling you, Princeton wants to. This is a software update. This is this is what no, not on my watch. Right. So yeah. So exactly. So that's so you can get if you plot the percentage. So this is a faithful rotation. So you're going to get 95% of this. And the reason is that this V star is just the Dirac, almost the Dirac unrenormalized velocity, and just shoots up, and then there's no, this coupling doesn't matter anymore. And that's why these bands, the flat bands here, remain flat. Only they change only a little bit around the gamma point. Excellent. Thank you. Very good. Yes.
Just for the title of the last slide, like, is it only like, I guess you did unity transformation, that means the VM model should be topological having Fermion for basically every angle?
Well, the VM model is topological for every angle, but the problem is that at different angles, you don't have this nice separation of just two bands versus this type of band structure doesn't. So if I take a projector into the VM model at any angle, at any energy where I have gaps, okay, I'm going to get topological Wilson loops, flow, etc. The problem is at different angles, you're not going to have these flat bands. They can just even do this. Some angles is very hard to find gaps. So that's the issue. You can't make this transformation at every angle because I mean you can make it, but it's going to be useless. Some of these F electrons are not going to be localized anymore, etc. Make sense? Very good. Thanks. Okay, so this is the largest energy scale of the problem. There's some other energy scales. So it's not really just a Anderson pure normal Anderson model. There's some changes, and the change is, you have this topological fermion C electron, and you have some extra interactions which show up here, which usually the way they're going to be treated, these ones are going to be mean field. This one is not going to be treated in mean field, and that's it's going to be treated in different ways by different authors, as I'll show later. But basically, this one is where you get self energies from Hubbard bands, etc. The rest, because they involve the C electrons, which are highly dispersive, you can just sort of treat them in mean field, hopefully. So now let's see what this model is, just looking at what this model does, interacting, looking at this Hubbard U. Okay? And there's several authors that pointed this out that are given here. But what this model does with Hubbard U is that these flat bands, which were sitting at zero energy in the non-interacting model, don't like to sit at zero energy anymore. So let's think about there's two flat bands per value per spin. There's 8 of them. Let's say the filling 4 or filling 4 from the first gap, so filling 0 from charge neutrality, right? And fill from -4 to 4 electrons, filling 0 at charge neutrality. The Fermi level sits here. The flat bands, which were non-interacting, set here, they don't like to sit to stay at the Fermi level because they will cost a lot more energy than having them move up and down in a symmetric way, which we'll get to later. And then starting from here, this Fermi energy is here. These actually, you see the mass, this mass between the C electrons is very tiny, right? So I can just think of it as 2 Diracs at the beginning. If I make this mass 0, this really becomes 2 Diracs. And this is zero hybridization model, meaning we made this term, the direct hybridization between F and C 0. We can add it later. But in this model, you can solve everything exactly because things, right, is just decoupled heavy degrees of freedom, which have many conservation laws on site. So it's an integral model and some dispersing electrons. So when they don't have hybridization, just like the Anderson model, we can solve things exactly in this case. And the physics is kind of the following. You go away from charge neutrality, you move from charge neutrality up. Now, because these F electrons have gone up and down at Hubbard U, okay, they don't like to sit at the Fermi level. When you move up or down, you're not going to hit the F electrons first. You're going to hit the C electrons first. And this is given here by the filling of C. So you go down, I hit the C electrons, you can see, and I raise their filling of the C electrons. This is the orange here. the filling of the F stays constant at 0 really means 4F electrons filled, but it's measured from charge neutrality, so it's 0, up until my Fermi level reaches, for example, here. Okay, when it reaches here, there's going to be an inversion, because when it reaches here, it doesn't become energetically favorable to move the Fermi level across this heavy fermion and fill the dispersing C electrons anymore, right? Because I'm just going to start more energy. So then you have a transition where the occupation number of the C electrons and that of the F electrons jumps. And it jumps by exactly 1, resets the Fermi level, and then you move down in this seesaw pattern. This is like a quantum dot plus a dispersive mode trying to fill them. So when you look at this region, we see that we got sort of 2 types of regions where we have local moments, which are these integer regions, and regions where we have fluctuations between the F and the C electrons, which is roughly around when these recalibrations happen in between the charge of the F and the C's. And you ask, in the symmetric state, what does this model predict at charge neutrality? Well, it predicts this spectral function exactly at charge neutrality, but really not this spectral function, because this spectral function is without any hybridization between the F and the C's. I didn't turn on the gamma, right? So now I'm going to turn on the gamma. What's going to happen? Well, these are the C's, these are the F's. The only place where things are going to happen are the level crossings here. So I'm just going to get this plus some level crossing here. So these gapless points are going to split. So let's find the spectral function, and moving a story forward. This is DMFT by the groups of Welling, George Savaranian, Rosa Valenti, Gautam, and also Dimitri and Lorenzo Kripa. But basically, I don't think it shows very well here, but basically you can see this picture is this picture just enhanced in the color scheme that was used by Shahalimani, just to make sure I get the same color scheme. You can see there's some Hubbard bands here. These are just these bands. These here, you can't see it because of the contrast, but these are just these Diracs here, okay, this double vortex here. Now, this splitting is because we put in the hybridization between the F and the C electrons, so they split. So you can see Hubbard bands, double vortex here, double vortex. If this M was 0, would really be a double vortex, Hubbard bands, etc. So the spectral function, if I just focus from minus 20 to 20, it looks like this. Okay, so it looks very different than the single particle band structure. The single particle band structure, I just draw it here, has a gap between the 2 bands at the gamma point. This is gapless, the interacting one. The band structure, the single particle band structure, has a gapless point at the K point, the single particle one. This is gapped. Exactly the opposite. So the moral of the story is that if you were able to measure the spectral function at large angle, or angle 1.3, not the magic angle, you'd see the non-interacting band structure, i.e. gapless at the K point, gapped between the states at the gamma point. If you now go to the interacting magic angle, you would see exactly the opposite with a measurement of the Hubbard U between these Hubbard bands. So now this is a screenshotted version of the quantum twisting microscope data. This is quantum twisting microscope on twisted bilayer, where the tip is basically flat and they can get coherence over, I don't know, microns. And then they can Fourier transform it and get the spectral function at 4 Kelvin, supposedly not in the order state. For the 5 Kelvin, I don't remember. At large angle 1.3, they do see exactly one interacting band structure that I can show here. At small angle, they see this spectral function. Now, the K's they're lined up. This is K. This number is 35 electron volts, which matches quite well with this number. And you can clearly see some region that becomes gapless resolution pending, more here, where you can clearly see the gap bands. Now, this was, right, this is unpublished, this is published. Okay, so the claim is that, this model might not be completely wrong. And then what do we do? So that was integer filling, but then what happens away from integer filling? Okay. We'll go back to integer filling a little bit later, but just to give you a little hint of what might happen away from integer filling. At integer filling, as you'll see on the next slide, at least at filling, at half filling, you see you have a small mass here, right? This mass, this m value is 8 electron volts, or 4 twice times n is 8. So if I make it exactly 0, then I'll just have 2 Dirac electrons. Okay, one on top of each other. This double vortex becoming 2 single vortices on top of each other. Same topology, but the moral of the story is my Fermi level here. I have very low density of states, so I won't have Kondo or anything at the Fermi level developing, right? Everything goes away from the Fermi level. But if I go to finite filling or non-integer filling, then, for example, this is at filling 2.3, you will see that because you have some density of states at the Fermi level, as you lower the temperature, you get a resonance at around the Fermi level developing. Okay. And this is what we claim is a Kondo resonance. Now, coming back to the 2 Dirac point behavior at integer filling, half filling, Pierce has a very nice paper where he points out in something that obviously we didn't realize that there could be a non-Fermi liquid behavior there. So this electron at integer 0 filling here is a Dirac electron. Okay, 2 Dirac electrons really. So its density of states is neither gapped nor finite. Okay, it goes 0. So there is a non-Fermi liquid fixed point that, in fact, if the mass is exactly 0, it can never have a Kondo behavior. It can never have a peak developing at Fermi energy, but it can have non-Fermi liquid behavior, which could possibly explain the linear T resistivity that Timaev sees in these systems. Now, I'm not claiming that we're doing transport that we can compute the resistivity, and this would start to gear up based on this idea, but hopefully, hopefully it can explain the resistivity that Timaev sees in samples, which is linear up to some scale. That scale will be given by the mass, that by the small mass that develops. Now, I want to go to point out some STM spectra and to show you how, show you kind of STM in the first generation, and then what comes out in the theory, the match of the theory in the first type of theoretical calculation, then the second wave of matching, which I think is much better. So the STM spectra look something like this. Okay, this is the gate voltage by which you change the filling, and this is the bias voltage by which you change the energy that you tunnel away from you. And you can kind of see immediately the appearance of these Hubbard bands. Okay, that I was talking to you about. You change the density of the gate, and you get closer or further away from the Hubbard bands, and you can see them here and here, etc. But then you can also see something that's stuck at the Fermi level. Then you can also see, and this is something that we weren't able to reproduce earlier, but we are now, as I'll show you. You also see some gap here of the order 10 electron volts, something like this. Now, if you do the STM spectral function on the heavy Fermion model as it was before, you're going to see these Kondo peaks as I showed you. You're going to see the Hubbard bands, but there are several things which you're not going to see so far, which is like this gap here. This gap is not a correlated gap. This is too large, and at too large temperature. Okay, so now let me go to a newer experiment on the Kondo peak. So we're gonna try to look, I'm switching between bilayer and trilayer, but it doesn't matter for now. We're gonna try to look at the behavior of this guy here with the temperature as you tune up the temperature. Okay, so at some non-integer fitting. So this is fitting 1.25, whatever. Theory tells you that as you go, forget about these scales. We don't fully trust these scales, and neither should you. So, but as you go from high energy, high temperature to lower temperature, you see the development of this on the peak. Now, this is the spectral function computed, and what you see is at low temperature, it sticks to the Fermi dose. Condor or mixed valence depends on how you want to call it, but some peak at the Fermi energy. As you increase the temperature, two things happen. This peak starts becoming more and more broadened, and the broadening is much faster than the temperature broadening, which I can tell, and it goes off, it disappears in one direction. It depends from the Fermi number. This is the STM data from Stefan's group. You can see this peak, the dotted line is thermal broadening. So you can see this peak disappearing much faster than the thermal broadening, and also disappearing in one direction. But that's, I wouldn't say proof, but certainly matching this. These are the Hubbard bands, as you see them here also. Okay, then up to no strain and up to no, not adding strain, there's several works that basically get similar behavior. Actually, Christian Halle and Eva actually had an early paper on some heavy fermion behavior with a different model, but basically they saw a mod gap. Then there's Lenny Bascones that has similar STM images as this, basically, and Pierce, Lasong, and Chandra Sarma, basically. There's and Sid Parnashwaran. There's many people that see or predict these type of symmetric state behavior with Hubbard bands. There's one thing that's kind of overarching over all of these papers, and that's the fact that the compressibility, if you compute it in this model, at least in DMFT, etc., seems to have peaks, right? Compressibility seems to have peaks at integer fittings, even at high temperature, okay, in these models. So it has peaks in the symmetric state, but at integer fittings, even at high temperature. This is not exactly what's in the experiment. In Shahal-Islani experiment, for example, the peaks are not at exactly integers, okay? They're a little bit away from the integers. And consistently, people, including us, have not been able to get the peaks away. Now we're going to claim that that's a strain effect, or think, or at least they say the strain can give you that. So what's happening in real samples is that the model is not as simple as this continuum model. Okay, that's usually the fact of life, but turns out that you can get a model with relaxation. What these things do is you twist the samples, the atoms move around. Okay, you have 10,000 atoms per Mori unit, so they move in certain directions. You have to figure out relaxation. Then you have some strain. Most of these samples have strain in them. In fact, you have to work hard in STM to find samples to find regions of zero strain. Okay, so normally if you work in this continuum basis of Bisset and Don, you can get all these strain effects and relaxation effects. The price you pay for that is the introduction of a large number of coefficients of terms. Now, if you work in the heavy fermion basis, the price that you pay for adding the strain effects and the relaxation effects is minimal. Relaxation effects break particle hole symmetry. So the only price you pay for introducing relaxation effect, once you take these continuum models, you project them down to the basis, is a difference in the chemical potential of the F and C electrons, just a diagonal term. Okay. When there was no difference between the chemical potential of the F and C electrons, the system was particle hole symmetric. Relaxation breaks particle hole symmetry. All these complicated terms, you project them to the fermion basis. You just get a diagonal term of a chemical potential that's different for the F for the C's, and that's basically your relaxation. The strain effect, you also find that its most, this largest term, once you project to this basis, is the splitting of the heavy fermion bands. So the strain effect, just because of these heavy fermions make up 95% of the bands. Strain acts mostly on them, and the only term that you have in the Hamiltonian, once you project to the heavy fermion basis, is a term that splits the heavy fermion bands. So this is how the band structure looks with strain. Strain plus this is strain. You can see the heavy fermion split. There's 4 here, so 1 per valley per spin here, 1 per valley per spin here. Together they're 8, but now they split. C3 symmetry was broken. C2T is not broken, so there's still some Dirac nodes. They're just not on high symmetry points, so I haven't drawn them. We haven't drawn them here. Relaxation breaks particle symmetry, so you get to these bands that look like this. We'll come back to this later, related to some experiments by Amir. But then you add strain plus relaxation, it looks like this. The blue and the gray curves are the Pistis and McDonald continuum type models versus the heavy fermion representation. You can see that it's excellent, and the heavy fermion representation just has, you know, 1 extra chemical potential for this and 1 strain term for this. You basically have 2 terms roughly. So now we can ask, well, what type of physics does this give? Okay, and let's go to the symmetric state. And let me show you some remarkable data from Eva's group that basically tells you several things. But in the symmetric state, what do you expect? Well, what you'd expect is that, let's say I'm at charge neutrality here, okay? Then I'm at charge neutrality. Now I split 8 heavy fermions, right, into 4 plus 4. So at charge neutrality, I should see an entropy of log of 4, choose 4, right? Because I filled all of these ones. The band, almost the band is selected. I still have some Dirac node, but it's almost the band at charge transfer. So in terms of filling the heavy fermions, very low entropy. Now I should see plateaus at every filling. For example, if I fill 3 of these 4 fermions, I should see log 4 choose 3. If I fill 5 of them, I should again see log 4 choose 3. But at some higher energy scale, okay, one should restore the U8 symmetry, and the entropy should be log of 8 choose whatever number you fill it. Now, of course, this is in hindsight, but if I take that thing first, you can see the entropy of different fillings, and you can see the match with the you know, there's just some simple counting of filling the heavy fermions, and you can see 2 plateaus. And the first plateau is consistent with the strain. This is log of 4 choose n. And there's a second plateau, which is log 8 choose n. Normally, the second plateau should go much higher in temperature because it's the Hubbard U scale, which, you know, should be 3 times the strain scale, or 4 times this, 3 times something like this. But we claim that at least this back of the neural calculations, phonon start taking over and after some region here. But you can see clearly 2 entropy plateaus that match quite well with this simple log counting. Next thing, there's also in this strain vein of understanding what's happening with the data. Next thing is to understand a little bit better the STM spectra, and especially this gap that's happening here at high temperatures in between, for example, the Condor peak and another upper band. Okay, so the Condor peak here actually turns out to be split by strain, and this is a DMFT calculation by Malcolm, etc. And these PIs that basically now shows you much better agreement with the STM data due to strain, and even the energy scale of strain is roughly 10 electron volts, matches perfectly. As a result of adding strain, what you also see is that the compressibility peaks have now moved away from integer filling. So now this is the finite temperature compressibility outside of the order states, and they moved away from integer filling, thereby solving one of the mysteries that we always had before of how this model just gives you compressibility at integer fillings. Okay, so what we claim is these are strain effects, and this is still the symmetric state. Now let's lower the temperature and try to go into symmetry broken states. You're going to go into symmetry broken states at integer fillings or a little bit away from integer fillings. And there's several symmetry broken states that you can go to that are all very close to each other in terms of energy. The reason for this is that this interaction of the heavy fermions is basically U8 symmetric. Model, the kinetic terms break U8 symmetry, but the system is almost U8 symmetric, and those are the low energy spin waves that you are seeing, those flat bands. There's the fact that they're so low energy, it's just U8 symmetry that comes in. Of course, the pure goldstone, which is the one is some breaking of U4. The symmetry is not fully U8, but it's almost U8, so that's why you have the low energy. Now, because it's U8, you have many degrees of freedom and many types of symmetry breaking. And at the beginning, us and a lot of other people predicted this type of symmetry breaking where you get a full gap, which is called KABC, and VP plus KABC at mu equals 1, etc., where you get a full gap. This full gap in the spectrum at charge neutrality, for example, would tell you immediately the symmetry is broken, because this double vortex cannot be broken, cannot be gapped unless you've broken some symmetry. What would the term they would break in the Hamiltonian was, in the interacting Hamiltonian, would be this spin term between the F and the C electrons. Doesn't matter. Turns out all of this was not correct because we didn't add strain at the beginning. Okay, and the people that made the correct prediction were Steve Kwan, Nick Brody, and Sid from Meshwaran. They basically added strain to this specific Doppler model, and then did Hartree-Fock, and they then found that the system goes into the symmetry broken state that is actually modulated at the Morris scale. It's called an IKS state. It's still intervalley coherent state, the spin singlet, but it's modulated. It's got some modulation on the Morris scale, and this state gives you a gapless system at mu equals 0, or this type of analysis is not, it's IKS at mu equals -2. But mu equals 0 gives you gapless state, mu equals 1 gives you gapless state with some Dirac electrons. So these would be like pseudo gaps, and mu -2 gives you a gap state. So these are actually our plots. We're using the heavy fermion model. We can obtain the same states as they did earlier on. But what I would say that we can very easily obtain was, not some 2.0 details of what was seen in experiments before. And this comes to Amir's data, is we can now understand from this model very easily why the insulators are stronger on the electron side always than on the hole side. And this is kind of counterintuitive, because on the electron side, you can see that the single particle band structure is actually more dispersive than on the hole side, but the correlated insulators are stronger. So I don't have actually the time to go into the details of it, but it has to do with the chemical potentials of the F and the C electrons. And you can clearly see that the simple calculation, this is a one-shot Hartree-Fock calculation, so you can do it analytically, which is good enough, can give you a larger gap at +2 than at -2. Okay, that is basically consistent with what's happening in the STM data. Now, the last slide that I have is what's going to happen to the cone peak. So at low temperatures, right? So at low temperatures, this is STM data. The Kondo peak, which was here at high temperature, you can see it here, orders and becomes two separate peaks. Okay, you can see it here and here. And these peaks are the gap opening that you see here. Now, when the Kondo peak orders at some temperature, the STM sees modulation on the Morris scale. So it sees the IKS state. So what happens is that you lower the temperature, you get the condo peak out of the, or the mixed valence, whatever you want to call it, peak at the Fermi level. Below, at a lower temperature, you get the order state IKS, which develops out of this. It splits this condo peak into two, for example. You can clearly see them here. And turns out that at even lower temperature, at non-integer fillings, out of that develops a second gap, which we believe is the superconducting gap. So there's a kind of gap scale energy, scale sequence, which starts from the development of something at the Fermi level, the splitting of this, whatever you want to call it, conductive or mixed valence at the Fermi level, and then into the IKS state as you order down, and then you go into another gap that's even lower, which is the superconducting
Right.
gap.
The IKS state is still a singlet state.
Just been saying that around U goes to two. It says, yeah,
So is that a modulation of the hybridization, or how should you think about it?
yeah. So it's not a density state. It's not a modulation. So total density is still fine. So basically, the way you think about it is you take one valley. You take the heavy fermion in one valley.
Yes.
And Dimitri, you can correct me if I'm wrong. So first I gotta be wrong. Because that's let's see. So you see you have these, you have a value. Let's forget about spin.
Yeah.
But let's take valley 1 and valley, this is valley K and valley K prime. Right? They kind of sit, I'm just putting their momentum
Okay,
together.
yes.
Right. Now you take valley K, and then you have the heavy fermions at some, okay, separated by U. And they're not exactly, I hope this is not permanent, but okay. Kind of fun. So they're not exactly, so they're somewhere here because you're not exactly at charge neutral,
Yeah.
you're at 2. So then the IKS state is you take valley K and you momentum shifted by Q. You take valley, the F don't care about the momentum shift because they're just filled. You take just the C scale, you take the K prime and you shift it by minus Q.
Yeah.
And then, I'm exaggerating the Q's. And then when this node, this Dirac node, that's right. So the nodes were here, but when you shift them, they're gonna have another.
Yes.
When it crosses the heavy fermion, it likes to hybridize because it gains energy. The Fermi level will be here. So it's a shifted state where the valley K has been shifted by some momentum Q, which you can. The momentum Q is a variational parameter, but we have expressions of it in terms of covered U, gamma, etc. So you shift the momentum Q, valley K in the Q direction, shift valley K prime in the minus Q direction, and then the Q is dependent. The Q is derived such that this node where now these two touches the heavy fermion, and then you open a gap, and that's the state.
So this Q is due to strain and you.
Yes.
And it
Yes.
is much smaller than the molecule K.
This Q is about it's about 1/3 of M. So it's not that much smaller. It's about 1/3 of M because strains in the electron volt. Strain is quite large, right? So the IK state is not the ground state, it's zero strain. At zero strain, it's either the KADC state or some other stuff with relaxation. It's not the ground. But as you put in strain, it immediately starts gaining on that. And the reason you can understand this reason just by drawing this heavy fermion and this shifted rocks in the two valleys and just playing around with just where the levels intersect and open gaps. And it starts gaining on strain, and at some point it becomes constant.
You're assuming uniaxial strain.
C3 breaking strain, yes, uniaxial.
So if you have triaxial strain, this could become more interesting.
If you maintain the C3 symmetry, then I don't think this is going to be a ground state, right?
Yeah, because then you don't split the.
Right. So this would be the ground state only when you break C3. You have to split the F nodes. like, you have to get, so it should be the ground state when you see your log 4 choose n. Or below that. And it kind of makes sense because, for example, right, I mean, okay, it could happen even in the order state, right? You see zero entropy, right? A spin, right? So, but maybe it's a spin singlet, but actually everything is at zero entropy, right? But anyways, okay, so since you see log 4 choose n, there should be a lot of strain. So this should be the ground state and low T. Okay, so with that, I wanted to thank you for your attention and to claim that we can sort of, there's a next level of TBG experiments, which, we still haven't solved any of the puzzles, superconductivity, for example, but at least some of the things that, some things that were puzzling can be sort of explained in some sort of coherent way, hopefully, depending on what you think of the star. So thank you.
Okay, that's a very comprehensive review of the heavy fermion approach to Python. Yes, Laura.
Thank you very much. You explained a lot to me. I really appreciate it. So I just have two questions because I come from the heavy fermion side, which is this splitting of the canopy at low temperatures due to strain, right? And
So there's two. So at high temperature, it can be split due to strain. At low temperature, you can go to even if you go on to STM regions that have low strain, at low temperature it should still be split, but that's by ordering. So there's regions of the sample that have lots of strain, they already break C3 symmetry by strain, so not spontaneously, right? So those ones don't need to, that one can be split even at higher temperature. The one that at lower temperature, you can split it spontaneously, you can break that symmetry, for example, C3 spontaneously, even if it wasn't broken, even if you're in the region of the sample with large strain, you can break it spontaneously and form these order states out of what you have at the Fermi level, out of the.
yeah, I guess
I'm not sure if this condor mixed valence, there's terminology in the heavy Fermion that I don't know, but it is.
yeah, that's helping. And you don't really see this in heavy fermions, but the other question I have is that
There's more flavors here. There's many, there's 8 flavors here, so maybe that's.
Yeah.
Maybe that's the reason why you can see more splitting than you usually.
Well, it's almost like a crystal field splitting in a way.
Yeah.
Right.
Is what illustrates.
Yeah. Right.
Yeah, that's
Yeah.
interesting.
Yeah.
Right.
And then the other question is that you always measure an asymmetry, at least in the planar tunneling. And in point contact spectroscopy in heavy fermions, and that's because you have a Fama resonance, and I'm not seeing that asymmetry here, or maybe I just don't know how to read color blocks.
Oh, the asymmetry between the
So the density of states will always have an asymmetry due to the Fama effect of
This
this.
is more like Argus, right? This is like a single point.
Yeah, this is a spectral function, the imaginary Briggs function with whatever broadening of DMFT broadening. So if you're talking about asymmetry between the Hubbard bands, so you see there's a Hubbard band here, and there's massive asymmetry between.
No, in heavy fermions, there's a different tunneling into the C's, of course, there's the F's.
Okay,
But that
okay.
doesn't really apply here.
So what happens is when the
Well, you.
localized states
I see.
take itinerancy,
I see.
then you get the Fano, and I get,
I see.
so it's a mixing of the ether and convection.
I see. Well, right. Okay. I mean,
There's somewhere, I just.
yeah, I don't know. Do you know the answer?
I think this should come through the matrix elements between the STM tip, right?
Which we haven't put in.
Which we haven't put in here, but it's very different from conventional heavy fermions because here we can't tunnel directly into the F electrons, right? Because the F electrons live at the A side, right? We can tunnel directly into those.
Mhm.
So that's quite different from.
Okay. Thank you.
Remy.
Thank you for a lovely talk. I have a question. Can you give us a flavor for why Hartree-Fock works so well in the system? Because in most strongly correlated systems, we have to go beyond Hartree-Fock.
Yeah.
But you seem to be able to get very good agreement with the experiment.
Yeah, so that's, well, at least at low temperature, right? So Hartree-Fock would never get to the Hubbard bands at high temperature, right? So all of the stuff at high temperature, there's no way. I mean, Ehresberg did at the very beginning, right? So at half filling, you can do sign-free Monte Carlo at half filling of the system. So he did some sign-free Monte Carlo calculations at the beginning. I mean, actually, it was after the whole thing came up, and basically about 2 years afterwards, he did some sign-free Monte Carlo. He was seeing the Hubbard bands because that's the exact method, right?
Of course.
So he was seeing that, but if you do Hartree-Fock, you're not going to see them. You're gonna, so, but why it works at low energy so well is let's now take these bands, okay, and say I have like whatever, and now let's work just in a projected. So let's say, you know, we don't know what U is. You know, if we compute it, U is about 1.5 to 2 times this gap. Okay, but you know, let's say I put some higher epsilon and U is smaller than this gap, say it's 0.7. Okay? Then I can just project into these bands, say, okay, if I want to understand Hartree-Fock, can't do it for other reasons, but if I want to understand. So then the Hamiltonian, if I just project Hartree-Fock, the Hamiltonian will become some V of Q, because it's some Coulomb, operator Q, operator, where this operator is the projected density. So you have C dagger in the bands, CK of bands M times the wave function of the nth band and the wave functions of the nth band. At K plus Q, this is at K plus Q, and this is at K. So this is the projected density to these bands. Now, this Hamiltonian, you can immediately see that it's positive semi-definite because the Coulomb interaction is positive semi-definite. Because it's positive semi-definite, if you find a state that's killed by OQ, it will be the ground state. Might be more than the ground state. So Hartree-Fock, at an integer filling, the Hartree-Fock ground states are killed by Q. It's like quantum Hall ferromagnetism. It's exact. So then I would expect it to be very good when I add some dispersion, etc. It's just basically because at integer filling, it looks like quantum Hall ferromagnetism, which is exact. Yeah, then you can prove exactly that it's the, now it wouldn't tell you anything about the Hubbard bands at higher temperature, but that's why I think Hartree-Fock and it works for any flat band that when you project into it. If you have some quantum number like at integer fillings, it will be exact Hartree-Fock because the state of the terminal state is the ground state just because of the positivity. A positive semi-definite, exactly. Exactly.
Thank you so much.
Thank you. Yeah.
Great. Great. On the subject of the integer fillings, so you mentioned a couple of states like intervallic coherence, right? So I'm curious how maybe we should compare the nodes later. We've done a basic Hartree-Fock calculation on an 8-band model that doesn't include the effects of relaxation. So of course it's simplistic. We wouldn't see
8-band.
So 8-band model.
That's pretty good.
So yeah, so that includes not just sort of the F, we don't do any projection, we do the things with Hartree-Fock, but also we don't just assume some effective value. We sort of derive this the integrals from ab initio, the bands. So then you have also the pair copying, the exchange terms, the direct, the indirect terms. Of course, it's all the level of Hartree-Fock, which, as you nicely explained, might have grounds to believe for one as well. The upshot is that we find lots of states that are absent from, if you just take this list of Donald and Jack to itself. In particular, we find lots of orbitally polarized. This, I mean, you have this orbitals, you have this px, py, and you find spontaneously there's a x and y. So there is orbital lifting.
So that will break C3 symmetry, right? So it's probably you do find out.
It's actually some.
These states should be at low energies. There's what I agree with you. There's a huge amount of low energy states in this system, including this. You know, the IKS is not that far away. You can 5 million electron or 5 million. What's the strain that can stabilize the IKS? Even 5 million electron.
Yeah.
So you know, it's very close to. It's way. You know, Hubbard scale is 50. If you derive from ab initio and project to its bands, about 50 or to 100, right? And then you get the state within 5 million electron volts. that are polarized, right? Because this C3 will basically polarize into one heavy fermion. Right? So I agree, they should all be close, but they should be, maybe this one will not find it as, the problem with this Hartree fault, as you do it like this, analytically, is you can only find the ground state exactly, because you find this, you can find some excitations, but there's a lot of low energy states that it's not exactly solvable Hamiltonian. So you can't, so I agree with you that if you have to they might be very close, many states very close together.
I may add a question. Can you say something about fractional filling?
Yeah, so all of these, fractional rational or fractional fractional?
Fractional, like 1/3.
Yeah, so this is, where was it? This is 1.25. Is it fractional enough?
Well, can your model say something about fractional Chern insulators, things like that emerge?
Fractional Chern insulators are very hard. Because they're not, right, they're not, yeah, so you can't get the fractional Chern insulators in DMFT, etc. Right? They're just a local. Now, the methods used for fractional Chern insulators and for Hubbard bands are kind of like, right, they're just separated by a massive divide. So the way I could say something about fractional Chern is what you've already done. Is basically we know they don't stabilize at zero field. You add a magnetic field, and then you conjecture that, well, you see them in experiments, so that's not a conjecture, but you conjecture that that magnetic field makes the Berry curvature flatter so that you can get, okay, that's a conjecture, right? So I can't do better at this than that conjecture. I could do better in terms of exact diagonalization. We could do better in terms of actually exactly diagonalizing the problem, making sure that that conjecture is true. But that's just that wouldn't give you much insight, I think. So I think most I can say about fractional Chern is what you found, that they exist here, but they only exist right around 3. Very, very hard to stabilize 4. So yeah, I mean, ideally there could be some methods where you mix Hubbard U and DMFT with fractional Chern insulators that they were thinking about. But two things are so far very, right? Fractional quantum Hall and DMFT are completely, so far as I know, like oil and water. I don't know.
Any last questions? I think everyone's hungry.
Oh, yes.
Thank you very much.
Thank
Andre.
you.